So in this video, we talk about memory register transfer language, RTL. So each of our instruction actually consists of a sequence of smaller instructions called a micro operation. The exact sequence of micro operation are carried out by an instruction can be specified using register transfer language, RTL. So in the Marie RTL, we use the notation of M with the square bracket H to indicate the actual value stored in the memory at the location H, and the left-hand side arrow to indicate the transfer of bytes to a register or memory location. So here an example of Marie RTL examples. So the RTL for the load instruction is the perform via three steps. First of all, the value of H will be placed at the memory address register, and then the content at the address H will be loaded into the memory buffer register, and value from the memory buffer register will be copied to the AC. Okay. Similarly, the register transfer language for the add instruction is performed in the following steps. First of all, the address H will be stored into the memory address register, and then the content at the address H will be copied to the memory buffer register, and then the value of the memory in the memory buffer register will be added into the AC, and then the result gonna be stored into the AC. Okay. So here's another example of Marie RTL with more complex for the skip cont instruction. So we recall that skip cont instructions skip the next instruction according to the value of the AC. So the RTL for this instruction is the most complex of our instruction set in Marie architecture. So basically the skip cont condition gonna be performed in the following step. So first of all, the Marie will check the value of the instruction register at the bit 11 and bit 10. So basically, if the bit 11 equal to 0 and bit 10 equal to 0, then we check the value of the AC. If the value of the AC less than 0, then the next instruction will be skipped, because the by increasing the program counter by 1. So the program counter will be equal to program counter add 1. So on the other hand, if the value of the bit 10 and bit 11 equal to 0, 1, then the we're going to check the value of the AC. If the value of the AC equal to 0, then the next instruction will be skipped. And the last condition, if the value of bit 11 and bit 10 in the instruction register equal to 1, 1, then if the value of the AC greater than 0, the next instruction will be skipped. We also have the condition that if both of the value of the bit equal to 1, so that's gonna result in an error condition. However, the additional condition could also be defined using the bit value as well. However, right now in the Marie architecture, that's gonna result in an error. So here the instruction processing cycle, basically the cycle including the fetch, decode, execute. That's the series of steps that a computer carry out when it run a program. So we first have to fetch an instruction from the memory and place it into the instruction register. Once in the instruction register, it will be decoded to determine what need to be done next, And if a memory value operand is involved in the operation, it is retrieved and placed into the memory buffer register MBR. With everything in place, the instruction is executed. Here the instruction processing in a flow chart. So first of all, we start, and then we copy the program counter to the memory address register, and then we copy the content of the memory address to at the memory address register to the instruction register, and then we increase the PC by 1. Then we decode the instruction and place the bits of the IR from 0 to 11 in the memory address register, and then we gonna check if the instruction require an operand or not. If the operand is required, we will copy the content of the memory address stored in the memory address register to the memory buffer register, and then we're gonna execute the instruction. On the other hand, if we don't need any operand for this one, we just go ahead and execute the instruction, and we come back to the cycle where we copy the values of PC to the memory address register. Here's an example of a simple program in the memory simulator. Let's consider the simple memory program given below. We have a set of mnemonic instructions stored at the address from 100 to 100 and 106, that in a hexadecimal value. So basically, this is represent the address, this is represent the instruction set in the program, and this is binary representation of the instruction, and the hexa content of the instruction stored in the memory. So basically, at the address 100 or 100, the load instruction will load the information at the address of 104. So basically, gonna be load the address. Computer gonna go into the address 104 and load the content of the in this memory address, just a 0 or 0, 2, 3 into the AC. Okay, so in binary representation, we have this 16-bit string of 0, 1. So basically, the most significant 4 bit right here represent the load instruction right here, and the remaining right here corresponding to the value of 4. 104. So basically, that's the representation of the 104 right here. This is 1, 0, and 4. So basically, that's the hexadecimal value. And in hexa content, this binary representation gonna be represented by 1, corresponding to the first 4 bit right here. That's 1. The next 4 bit right here gonna be 1, and the next 4 bit equals 0, and the last 4 bit right here equals to 4. So this is gonna be the instruction load at the address 104 gonna be represented by 1104. Similarly, we can see that the instruction add 105 is mean go into the address 105. Here, load the content in that address, that's FFE9, and add to the content of the AC, and then store that result back to the AC. So in binary representation, we have this binary string, and in hexa representation, we have this representation 3 corresponding to the first 4 bit right here. 1, that's gonna be the next 4 bit right here, 0 is the next 4 bit right here, and 5 is the next 4 bit right here. Okay. The next instruction will be stored at the address 102. That's store 106, so it means whatever we have at the AC right now, we're gonna store into the memory at the address 106. So the 106 right here, we have the nothing in there, so we just store the content of the AC to the address 106. So in a binary representation, we have the store gonna be represented by opcode 0010, and 106 gonna be represented by 0001, 0000, and 0110. Okay, in the hexadecimal representation, we have the 2106. And the next instruction is stored at the address 103. That's a haunt. So it means after all the operation right here, the program now terminate. The binary representation gonna be by this binary string. So the first 4 bit right here, that's the haunt instruction, and the remaining right here is all 0. So in a hexadecimal representation, we have the 7000. Okay. So that's a basic representation of the memory program in a binary and so in hexadecimal. So let's look at the what happened inside the computer when our program actually run. So let's look deeper into the load 104 instruction as we saw before. So basically, there's several steps that the computer will perform to for a single instruction load 104. Okay, so basically the first step is the fetch. So in this one, the program counter number gonna be stored into the memory address register, and then so the program counter gonna start with the address of 100, and this one gonna be the same for the next step. Now when the value of the PC copy to the memory address register, so the value of the memory address register will be the same with the value of the PC right here. Okay. So the next one, the computer gonna go into the address of one of the access to the go to the address of 10100 and copy the content and put into the instruction register. So now we have the content at the 100 is mean load 104, so the content of the instruction register gonna be represented by 1104. So the first number 1 right here represent the load instruction, and the 104 right here is mean the address in the memory the content will be loaded. Okay. On the other hand, the value of MAR gonna be the same, and PC gonna be the same. So the next step, once the information at the address 100 have been copied to the instruction register, now the program counter will be increased by 1. So PC gonna be PC plus 1. So that means the next instruction will be executed. Okay, so now PC equal to 101. IR gonna be the same, and memory address register will be the same. In the next step, gonna be the code. So the computer gonna be look at the value of the bit in the instruction register from 0 to 11, and that bit gonna be copied to the memory address register. So now we have that corresponding to the variable 104 right here will be copied to the memory address register. And then we're gonna decode what the opcode of the instruction represented by bit 12 through 15. So basically this corresponding to the variable 1 right here, and it means load the content at the address 104 in the memory to the AC. So the next one is get operand. So basically that's gonna go into the memory at the address stored in the memory address register. So right now gonna be a address 104. So that information will be copied to the memory buffer register. So we can see that at the address of 104, that's content gonna be a 0023 and will be copied to the memory buffer register. And the last step gonna be execute. So we can see that this load, that's a load instruction. So basically the content of the memory buffer register will be copied to the AC. So we can see that the content of the in the memory buffer register will be copied to the AC. So this is all step in the load 104 instruction. So here another detail of the second instruction add 105. So basically now we have the program counter have the value of 101. The instruction register have the value of 104. Memory address register have the value of 104. Memory buffer register have the value of 0023, and the AC have the value of 0023. Okay, so the add 105 instruction, first of all, gonna fetch the information. So the value of the PC will be copied to the memory address register. So basically PC now equal to 101 will be copied to the value of the memory address register. So now it's equal to 101 instead of 104 as before. The next step, the computer can go to the address of 101 and load into the instruction register. So we can see that the value of the in the memory at the address 101, that means a add 105. So mean a the opcode gonna be add instruction, and the data will be load from the address at the address of 105. Okay, so now the IR have the value of 3105. All other values the same. Okay. And next step is that the program counter will be increased by 1. So PC equal to PC plus 1. So now the value PC is 102. Okay. All other values are the same. The next step we will perform the decode. So basically the computer will look into the value of the instruction register a bit from 0 through 11, and that value bit gonna be copied to the memory address register. So we can see that the value of the instruction register from 0 through 11 gonna be have the value of 105. So 105 value right here will be copied to the memory address register. So now the memory address register have the value of 105. Next one is gonna decode the instruction by look at the value of bits from 12 to 15. So you can see that in the instruction register right here. So you can see that that value equal to 3. So it's knowing that this instruction saying that we will perform the addition operation, and the addition operation requires an get operand. So basically the computer gonna go into the memory at the address specified by memory address register. So that is the address of 105, and get the data from there. We can see that the data at address 105 have the value FFE9. So that value gonna be copied to the memory buffer register. Okay, so now all the data in place, we can perform or execute the operation by taking the value in the AC, add with the value in the memory buffer register. So you have the AC value right here, and gonna add to the value of the memory buffer register, and then we obtain the we obtain the new value. That's the addition of the this value and this value. So notice that this is the value in hexadecimal representation. Okay, so we add them up, we obtain this one, and this value will be stored back into the AC right here. Okay, so that's the step of the instruction add 105. So here the a simple example of Marie programming. So in this program, we write a program that perform the addition of value in x with value in y, and then we subtract the value of z, and the result gonna be stored in a variable named result. The value of x will be entered when we assign x equal to 10, y equal to 20, and z equal to 5. Okay, so all the variables are stored in the memory, and the result will be stored in the memory and printed out on the display. So how can we perform this program, or how can we write this program in a Marie simulator? So basically the first command we're gonna use load x. So basically x gonna be the value in the memory at the address x will be loaded into the AC, and then we perform add y. So it means the value of the value of variable y will be add to the AC, and then we perform sub z. It means the value of the AC will be subtracted by z, and the result gonna be stored back into the AC. And then we perform store result. It means the store the result will be currently at the AC will be stored to the variable result, and we output. This means display the value in the AC, and we have the haunt that terminates the program we are running. So we also have the declare of the variables. So we have the x with the type that the decimal equal to 10, y variable with the type decimal equal to 20, and z with the type of decimal equal to 5. And the result with the type of decimal equals 0. So these are all of the commands we need to write a program that perform the add of variable x plus y and subtract z, and the result gonna be stored into the result.